Hello, my name is Michaela Valdez,
And my name is Theodore Nicolau.
and we are discussing the role of turbulence in sediment transport in rivers. This presentation focuses on how turbulence affects sediment movement in rivers. Many of the concepts we will discuss are reflective of fluid mechanic fundamentals, like understanding fluid and flow properties associated with turbulence.
For the sake of a common understanding, we will define sediment as small particles of matter, such as sand or other earth matter. For high flow rates, the size of sediment may be larger due to stronger forces acting through the river system. In a river, there are different layers in which sediment is transported. Bedload is sediment that moves along the riverbed. Large sediment particles in the bedload roll or skip along the bed of the river, but do not stay suspended. Additionally, we have suspended load, where turbulence creates forces that lift sediment from the riverbed into the water flow. Lastly, we have wash load, where the finest sediment is suspended in the flow. Even with low flow rates, the wash load will usually remain suspended due to relative equilibrium of the buoyancy and weight forces acting on the particle.
Fluid mechanics is a simple way to broaden our understanding of how sediment is transported along a river. Rivers are open channel flows characterized by fluid flowing through a duct or channel that has a free surface open to the atmosphere. A few important things to keep in mind are the no-slip condition and shear stress along surfaces that offer resistance to flow and also flow separation. The Reynolds number for open channel flow can be found using this equation. Most of the variables should look familiar, like kinematic viscosity, average flow velocity, and fluid density. But the hydraulic radius is a ratio based on the cross-sectional area of the channel and the wetted perimeter or the channel surfaces that are in contact with the fluid. Naturally, rivers do not have uniform channel shapes, so the hydraulic radius allows us to analyze the channels as if they were uniform. If we calculate the Reynolds number for a river, we get a value near 50,000. The flow rate can be calculated by multiplying the cross-sectional area by the average velocity of a fluid. If the water is not flowing, sediment would not be transported along a river, but simply suspended in the water or settled on the riverbed. The moment when a sediment is moved by flow is called critical shield stress. Depending on the size and shear stress of force needed to remove a mass by a certain acceleration rate, the sediment will be transported in a flow. Here you can see the bed load moving along the surface of the river bed, along with the suspended load of sediment along the river flow. The mechanisms behind sediment transport are explored in the journal article, The Effects of Turbulent Bursting on the Sediment Movement in Suspension. On the bed of a river, turbulent flow acts along the rough, uneven surface and begins to lift sediment. Using a particle and flow imaging systems, they observe that sediment is often lifted in a discernible motion of bursting, which includes lifting, oscillation, ejection, as seen here, and sweeping of sediment over a riverbed, as seen here. To capture this phenomena, they coated flumes connected to a pump and flow regulator with waterproof sandpaper. Observed was an area mimicking flow separation called free turbulent area, along with a separated region below that, or trough turbulent area, acting as an ejection cushion that impedes sediment sweep and pushes sediment toward the suspended load. The most interesting part of this flow, however, is this vortex-like structure called Coik boils. These boils result from a low fluid pressure within the vortex that create negative pressure that can help suspend great amounts of sediment. This is why you might see little swirls along the surface of turbulent rivers, as Coik boils can often reach the free surface.
So far, we have been looking at turbulence and open channel flow for rivers. We can also analyze how placing physical objects into a riverbed changes the flow dynamics of the water. For example, the external flow of water around a bridge pier can produce different types of turbulent flow, which directly influences how sediment is moved near the pier. A study was conducted in 2018 at the University of Melbourne in Australia. This study analyzed scouring around bridge piers using numerical modeling based on computational fluid dynamics. The study analyzed how turbulent flow produced both horseshoe vortices and wake vortices. These two vortices were the largest factors responsible for the displacement of sediment around the bridge pier. In this image, we can clearly see the different types of vortices that are forming around the pier. The flow of the river when approaching the pier will flow downwards. This downwards flow will be responsible for the formation of the horseshoe vortex at the base of the pier, which can be seen down here. Also, water flowing around the cylindrical bridge pier will form wake vortices, which can be seen over here. The horseshoe vortices are responsible for lifting a significant amount of sediment off of the riverbed. Additionally, the wake vortices remove more sediment from behind the pier and carry it downstream. Both of these vortices act at the same time and scour the riverbed around the pier, which significantly destabilizes the foundation of the bridge. Here we have some velocity profiles of fluid flow around a bridge pier at different times. The flow of water is moving from the upper left to the bottom right of the image. So the water is moving, the flow is moving in this direction. The Reynolds number that was used for this simulation was 39,000. The velocity profiles help us see where different velocities are happening, where different vortices are happening. As the vortices begin to form, there is backflow that moves in the opposite direction of the river flow and starts to spin. So there is a reduction in the velocity that is shown by different shades of blue at the front and the back of the pier. So the different shades of blue are here in the back for the wake vortices and here in the front for the horseshoe vortex. So we can see that here that the flow of the vortices is slower than the surrounding free stream velocity of the water. We can also see the boundary layer separation happening a little bit past 90 degrees from the point of the incoming flow. So from this point, we have the separation occurring somewhere around here. This is a clear example of how scouring caused structural failure for a bridge. These types of mistakes are sometimes related to engineers not considering significant storms that may happen once every 50 to 100 years. The larger volumes of water moving through the river will cause deeper scouring and remove the foundation of the piers. Larger flow rates would require deeper foundations in order to support a given bridge.
As you might have concluded, this subject is important for many reasons. Sediments travel along rivers and are deposited at various stages along the way. Along with this sediment, things like nutrients, fresh water, and contaminants or pollutants are transported. If too much sediment is deposited in one area, water quality goes down, algae blooms may spread, and aquatic habitats may be insufficient for most species. If too little sediment is transported or deposited, aquatic life may not receive enough nutrients or be able to build up proper habitats. Erosion may also result along the river and at beaches where the rivers flow out to because not enough sediment reaches these areas that require vast amounts of sediment buildup over time. The placement of dams thus involves in understanding how sediment is transported. Typically, dams prevent sediment from naturally flowing downstream while it piles up behind the base of the dam. All these can lead to affecting food and water resources regional economies that rely on waterways, and how engineers design and build around and within river systems. Thank you, and we hope you enjoyed our discussion on turbulence and river sediment deposits.
Thank you for your time.